Welcome to the UMN Robotics Ri3D 2026 robot named Daedalus this year. My name is Alexander Tong. I am the integration and design lead for the robot, and I'm just going to walk over the high-level vision of this robot. Starting off, we worked on some strategies to figure out what would be the best strategy to build a robot for this game, and we ended up going through a few processes in order to essentially make 6 different robots and then vote on one as a team. But that robot that we selected was going to be one that was quick, fast, and could shoot from anywhere on the field. And that was kind of like the main important parts. And the way that we were going to achieve that was make sure that the entire robot was under 22 inches. We have Mecanum drive base, but the reason why we have that is because we can't afford to swerve. And the idea is that if we were a FRC team that could afford swerve, we would put swerve on this robot, as well as being able to hold a large volume of balls, because there is no limits to the number of balls that your robot can hold. So the strategy would be to essentially collect as many balls as possible right at the beginning of a match, and be able to shoot them over to our alliance side, which is why we wanted a turreted shooter that could shoot from anywhere on the field. The idea is that you can keep sucking up balls and shoot them back to the alliance side. And essentially we prioritize those major 2 components over having an advanced climber. We still thought that we could make a simple climber that would be able to get us to the traversal rung, which, as you can see, we ended up not being able to fully achieve that, but it was a part of the original strategy to make a simple climber, but not really focus on that component of the robot. Things that we didn't have as a priority for this robot strategy and its design was dealing with the bump on the field. We didn't do any design for that, much of any testing. We just decided that our fast robot was going to be able to be low enough to go under the trench, and that would be it. And as I mentioned, climbing wasn't a very big priority. And the other major priority that we kind of decided not to focus on was climbing as quickly as possible. If we were going to make a climber, it would be short, it would be thrown on the robot. We weren't going to do too many considerations of the CG and making sure that that was as stable as possible. And that was our trade-off. The overall structure of this robot that we kind of drew on a chalkboard before we fully made any of the mechanisms was to have an intake that went tall to the top of the robot, so then we could have that large capacity volume of balls stored in the robot. Then have a hopper system that would hold as many balls as we can, have an indexing system that would take balls out of the hopper and put them into the shooter, and then a turreted shooter that would be able to aim around anywhere in the field. Other things in this robot is all the electronics are located in the bottom of the robot. We're not going to flip it up and show you because it is a hot mess in there, Ri3D style. But otherwise, the wires are kind of just scrappily run everywhere else. It's mentioned in other walkthroughs about how even that caused some issues for our robot. And finally, I want to talk about some of the major optimizations we would make to this robot first if we were to redo it or rethink the way that we approach this robot at a high level. One of the biggest ones would be optimizing for storage volume and capacity. I said part of our original vision was to have a large storage volume, but when we ended up actually finally getting everything in CAD and not spending too much time redesigning things because we didn't have time to redesign them really, we ended up having less of a storage capacity than we wanted. I think we anticipated at least above 10, somewhere between 10 and 20, maybe above that balls that would be able to be stored in the robot, and I don't think we can store much more than 10 in this robot. So how we would achieve that optimization would be to drop the entire indexer further down into the robot. We would do things like the intake positioning, how things go around the climber, how compact the hooded turreted shooter can be. That is probably one of the first things we'd approach to optimize on this robot, just to get more storage capacity and just optimize these designs. Another thing that we would optimize is the software control of this robot. As you can kind of see from our video, there are some limited features. Our turreted shooter is able to shoot from different positions in the field, but it's not able to be as consistent, and it's not able to auto aim or auto correct for anything in the robot, just because software is not there yet. It's a robot that we had to make in 3 days, and we can only start shooting and testing the shooter within the last 24 to 48 hours. That also pertains to other components of the robot. We have some bugs with We had some bugs with controlling things that slowed us down, and I believe like gear ratios are what stopped us from moving the intake as mentioned. But there's a lot of software optimizations that can definitely be done to this robot. And the last like major optimization we do is, I kind of mentioned it, is the wiring. The wiring is causing like a decrease of functionality in this robot with us being able to not able to use the yaw on the turret. We do like important wire management and control, mainly through the use of cable chains, that when things rotate, cable chains are able to guide wires and not have them go anywhere on a rotational body. It's mentioned that the wiring packaging wasn't considered at the top of the shooter. That's another major optimization we make. And to wrap up the high level of this robot, just mentioning some of the illegal parts that would not pass a technical inspection that we just did not have the time to essentially fix with our Ri3D robot. One of the biggest ones is the turret. As I mentioned, we definitely optimize the packaging. And the biggest issue is that no matter how you turn this turret, there's going to be some rotation angle that you turn it at where components of the turret will be outside the frame perimeter, which, if we had any walls here, it'd conflict with that, but the bigger thing is rule doesn't allow you to extend in two directions, so that'd be an extension off this side, and if the intake is extended, that'd be an extension off this side. Another major component of that is our climber. There's a number of bearings, rollers, other components that kind of hung off the edge of the robot past the frame perimeter. That's also just a small thing that we talked about in the climber section.
Hey, I'm Isaac. And I'm Nathan. And we worked on software here for the UMN Ri3D Robot. So what we got here in terms of software, we're going to kind of just follow the path of the ball through the robot. The first part here starts with the intake. We've got a folding intake here that, when functioning, allows us to drop our intake from a starting configuration down to where we can pick up the balls and index them into a robot. You can see it like that. And we had a couple issues. We ran into some things with the Spark Maxes, but overall it's shown to be pretty consistent.
Yeah, the only issue that we had with this was our gear ratios were too small, so we weren't able to get this actuation. And then the next thing is the indexer. It has 5 slots for balls. The balls basically just fit in, and the whole thing rotates. And then that goes up to the flywheel. And the only issues that we had with this indexer is when there's balls stacked up high. It will jam sometimes. And the software running this is just a big Neo with a like 50-to-1 gear ratio and a 90-degree gearbox, just running duty cycle. And then after that, it comes up to the flywheels. The flywheels have a differential RPM, so the top spins faster than the bottom, so we can top spin. So our arcs are faster dipping to get into the top. And then the next thing is the turret. We have mechanical capabilities to do yaw. However, our wire management in this amount of time, we weren't able to get wired up to be able to rotate our yaw. But our pitch is just a big gear rack and a small gear traveling along it. And then Isaac, if you want to talk about how we wanted to implement vision.
So we didn't get around to implementing a vision or having it working by the time we filmed everything, but we have a lot of the code written, and ideally before a week 0 event we plan on going to, we might be able to get it up and running. But we've got a camera mounted here running photon vision on an orange Pi here, just powered by a buck converter. After kind of taking some measurements, we can figure out where the camera is relative to the center of the robot, and kind of how, when the turret shifts, how it affects the camera's position. And with that, we can do our 3D April take tracking. And if we have consistent location tracking of where we are in the field, we are hoping to be able to shoot from anywhere on the field, kind of within the scoring zone. So ideally, if there's a bunch of balls over on our side, we can drive into them, index them up, and continuously shoot into the hub while moving. So hopefully we got high hopes for that, and we'll kind of see where that takes us.
I'm Sam, and I'm here to talk about the intake. Our initial strategy with the intake was to keep a small structure so that there was more room on behind it for the balls, and it would also extend out more so we can grab in more balls at a time. So it starts in this configuration where normally it'd be lower and it would be below the trench, so we're still able to move it. Another benefit to that is that when we're holding balls, it holds them in there better so that if we get bumped around, the balls will still stay in there. So when we deploy it now, as you can see, it goes up fine. When it comes from the side, it will also bring it in. One problem that we noticed though is that the balls tend to get hung up on this plate. A solution to that would be to use bigger wheels, as these are 3D printed, and so you could make them to be larger. Another issue that we encountered while assembling it was the spacers. It was using plates, it's very important that we use the correct spacers, so my suggestion would be, if you're able to print your own spacers. That way the assembly will be quicker and easier. And another issue we kind of came across is if this flapped too much, where the ball wouldn't be compressed as much, but that wasn't as hard because you're able to adjust this easier with zip ties. The pivot is powered by 2 Neos that are 50-to-1. And yeah, up here is 3-inch wheels so that we get more compression to give the balls an extra lift up into the index for it to spin around. And that's it.
Hi, I'm Rashan. I work on the index. This index spins, and it has a capacity in the drum for 5 balls, but you can stack more balls on top of it. Can you spin it? So the reason these blades are tilted a bit is because we have a continuous spinning blade, or the blades are continuously spinning, and we have a spot for a dead ball. So this, the angle of the ramp helps the ball move out of the way, so another ball can push it up. And it also helps push it up this ramp in the back. The ramp in the back is just a couple of hex shafts with some bearings on it, just help the ball go up to the turret. The drum is moved by a Neo on a 50-to-1 gear ratio with a 90-degree adapter onto it. And the wall of the drum is made with these red 3D printed parts. They're just connected with a dovetail mechanism. And then we have some poles sticking out, and some polycarb walls sit tight to it. There is a jamming problem on the index when it gets too full. So test a solution if you want for that. And then you can also increase the capacity of the drum if you lower it below the top of your chassis.
Yo, I'm Tom.
Yo, I'm Nathan.
We're going to talk about the turret and yaw.
So our strategy was to be able to have a fully pitching and yawing shooter, so that we can just, anywhere we are on the field, we can just shoot there. And then Tom can talk about how we actually did that more in depth.
Yeah, so on the hood that we have here, we have helical gears on the side with a pitch angle of 30 degrees with metal aluminum 6061 in the middle to take the load. The helical gears are to align there's some slop because of just everything in the system and these, and so the alignment is still kind of rough. Also, we built this in 3 days, so there's imprecise manufacturing in the bottom that I think maybe adds to that. We did the same thing on the yaw mechanism, which is much better because the teeth are much larger. Unfortunately, the yaw also had many issues with spacing, where we have a Neo 550 on this side that kept running into conflict in where it was relative to the agitator down here. And the yaw also caused the entire turret to kind of conflict with this space, which we could use for a larger hopper.
Yeah, and then, so the pitch, I can actually move it for you. So this is how it looks when it moves. It's using a Neo 550 on a 10-to-1, and then it's around like the total ratio is around a 55-to-1. It has plenty of torque, and we're just limiting the speed because it doesn't need to be jerky. But then also the flywheels are on the turret, and the way that we found this compression in this wheels was we just tested one and it worked well, and then we just stayed with it. So we didn't have time to go and test everything, which I recommend that other teams go and do their own testing, because we just did our first test and it worked well enough, so we kept it. So this is the flywheels. They're driven by one of them is a Neo 550 and one of them is a big Neo. We were supposed to have two big Neos, but one of them like burnt out, so that's fine. They're just using 60-tooth belts. I would recommend that you look at your own spacing and try and keep everything, like all the weight is, there's a lot of weight in motors and wires that have to go on a moving part. You try to like belt everything so that motors can stay farther down and on not moving parts.
On that topic of spacing, we didn't really plan with all of the constraints here for motor or wire management and motor controllers, so they're kind of just thrown on here. That definitely contributed to the factor, the previous topic of why we can't currently move the yaw. That was kind of poorly planned out. Definitely recommend doing some research into how to get a turret to get wires to move nicely. Additionally, we had to cut off the tops of our large gears here, which to fit under the trench. That could probably be avoided by downsizing this entire mechanism to get more rotation, although it didn't seem like it was necessary when we were shooting.
All right, and to lead us out here, I'm Jacob. I'm the mechanical lead for the team here, and I'm representing the climb sub-team. This wasn't as big of a priority for us, so our prototype didn't quite come together quite as we would have liked, but we do have some interesting ideas here that I bet you guys would find useful. So this is made up of a Andemark elevator kit put together with 4 hooks here, 2 sets of passive hooks. These don't move at all with respect to the robot, and then 1 set of active hooks which go up on the elevator and do move with respect to the robot. The idea here is, as you can see here in this clip, so you can see that the center rollers go over the first bar as it goes up, and then they pull the robot up such that these passive hooks can go underneath and then hook over the bar again. And then from there, it keeps climbing in that same manner all the way up to the top, at least in theory. Unfortunately, we didn't quite get it put together how we wanted. The CAD didn't quite come together. The CAD is quite tight, as I'm sure you guys are starting to notice if you're going through your parts. One other thing we did is with the standard sort of tank chassis we had, we were able to mount the climber-in-a-box pulleys deep inside of the robot here with the motor behind it, such that we were able to get it almost all the way down to the bottom of the frame, giving us just a little bit of extra space in order to get all the geometry to work out properly. And the last thing to talk about with the climber is the sort of obvious illegalities here. We're sitting about 4 inches outside the frame perimeter here. And the way that we came up with last minute in order to figure out how to deal with that, we weren't able to implement it, is to have the climber actually tilt backwards into the robot when it's stowed. So we could, as you know, you can only have outside of the frame perimeter on one side. So it would be stowed until we actually need to climb, in case we'd stow the intake or the turret or whatever we needed outside, and then we'd be able to push it out to climb.